Okay, geometry as promised. We have a video coming here for lesson 8.4. I'm going to very quickly summarize the first half of this that we talked about yesterday in class, and then we'll finish up with just some of the examples that we didn't get to and the three parallel lines theorem, and then we'll be good to go. So first of all, we're now talking about some proportional relationships. That's what this is about. Understanding that once you set up two triangles that we know are similar, some interesting proportionalities begin to happen, and that allows us to solve for missing sides that otherwise we wouldn't be able to. So the first theorem that we're going to discuss is the triangle proportionality theorem. And this basically states that if a line is parallel to one side, if you create a line, in this example here, it is line TU, or a segment TU here, and you create it so that it is parallel to the third side, that it is not intersecting, then regardless of, whether it's all the way out, very close to this side, over here, it doesn't matter. As long as it intersects two sides and is parallel to the third side, then it will divide up our sides proportionally. So sometimes students are like, oh, it's like a mid-segment, and it is, except a mid-segment definitely only goes through the midpoint. It's connecting midpoint to midpoint, and it is parallel, and it creates congruent sides. These don't have to be congruent, but they are proportional because of this parallel relationship. So in this particular example, if TU is parallel to QS, then we can conclude not just that the small side to long side is proportional, because we already knew that based on the similarity of triangles, but more importantly, segment to segment. So QT here isn't really a side, but it is a segment here that is divided up by point T, just like SU is divided by U, and these guys end up being proportional to each other. So you could set up a proportion that says RT is to RT is to TQ as RU is to US. And you could do it this way and this way, or this way and this way. So we'll see a little bit of that. And so actually a good part of class was spent working on the proof for this. So if you have given that a shot, or you can press pause really quickly and try the proof that proves this in particular. So the first piece of the puzzle is to prove that the triangles are similar, because that is kind of where this is rooted anyway. So we can use angle-to-angle similarity here. Since these are parallel, we've got a couple of corresponding angles. And then by reflexive, angle R is congruent to itself. So you can establish that the small triangle here, TRU, is similar to QRS by angle-angle similarity. Once you know that the side lengths, these sides are proportional. So the initial setup is to set up this long side compared to the short, long side to short. But our goal is really for these smaller segments. So that's when we talk about the segment addition postulate. Once you've set up your proportion based on the fact that corresponding sides of similar triangles are always proportional, you can take QR and separate it out with the segment addition postulate into the smaller segments, substitute that in to that proportion, and at that point, TR over TR becomes just 1, and UR does as well, and then a little ESPO will subtract the 1, and we'll show that this always has to be true. So we spend a good time out talking about this particular proof in class and setting it up. But that's essentially your justification for why the triangle proportionality theorem always works. And that's the beauty of it. Now that we've proven it, we can just use a theorem and we don't have to make that argument every single time, right? That's one of the benefits. So go ahead and flip that over. We then talked about the fact that the converse is also true. So in the converse of that particular theorem, we know that if the opposite is known, for example, that segment RT and over QT is proportional to RU over US. So if that ratio is proportional to that ratio, then the two sides here must be parallel. So it goes in both directions. The converse just switches that hypothesis and conclusion, and then we can prove the sides are parallel if necessary. So here we practice just a few examples. Again, feel free to pause it, like I can cover it right here if you want to pause and try them. And then you can check your work. But the idea here is, since we know these are parallel, we know that these smaller segments that are created can be set up as a proportion. So you can see here we did, we're looking for x. According to this, what is the length of VW? If we know that this is parallel to that. And so we set up a proportion in class that said, okay, 10 to 8, that ratio must equal the same as x to 12. And so we set that up, cross-multiplied. You could either cross-reduce like I do. Some of y'all don't like that, and that's fine. You could just do 8 times x is 8x. 10 times 12 is 120. Divide both sides by 8. You'll still find out that this length must be 15. So that has to be 15 because these have to be proportional. Okay. Same thing on this one. If you gave this one a shot, find the length of YZ for this particular case. And so since they show us that these are parallel, we know that the ratio of 44 to 35 must be proportional to 36 over x, or YZ, I guess is what we called it here. And again, cross multiply. 44 times our unknown must equal 35 times 36, which is 1,260. And then just divide both sides by 44. We find out that the missing side segment here must be 28.63, repeating. Okay, so that's kind of where we left off. Let's practice a couple of other ones. If you want to give this a pause, if you haven't tried it, try these really on your own, and then we can work them out together. Okay. Okay, so assuming that you have given this a shot, let's see how it went. So this part is absolutely critical. This is what's going to let us set up our proportions in the first place. The statement here tells us that AC is parallel to HG, and it's also parallel to FD. So that creates a set of shorter segments that can all be set up in proportions so we can solve for what we need to. Okay, so let's see. I'm going to start with the Y because that one's a little simpler. So always start with one that you do have enough information for. So really, these guys have unknowns and this has unknowns. So I want to make sure I set this up against that 12-8 relationship. So you could either do 12 over 18 is 8 over Y. You could do 12 over 8 is 18 over Y. Essentially, it's very flexible as long as whatever logic you used to set up your first ratio, you use the same logic as the other one. So on these, we went sort of side to side, and like did the 10 and the 8, x to 12. So maybe let's mix it up a little bit here, and you'll see you'll still get the same answer. Maybe we'll go from one side to the other. So this side that is made by FD, so the 12 over the 8, we could set that up, must equal 18. So if I started on the top here, I got to make sure I start on the top there. 18 over Y. And there's our ratio. Like I said, we could have also done 12 over 18 is 8 over Y. We could have done 18 over 12 is Y over 8. As long as your logic in your organization is consistent for both of them, there's actually several ways you could do that. Okay, so now that we've set up a proportion, we know the whole idea here is that if these are proportional, then this cross product right here will equal this cross product. And I like to do a lot of cross reducing, but I'm going to go ahead and avoid that this time and just kind of leave the numbers as they are originally. So 12 times Y is just 12Y. 8 times 18. So that's what we really need to work out here. So that's what, 80 and 64. So I think that's 144, but let's take a look real quick. And if we do 18 times 8. Yep, 144. Just wanted to be sure. So there we are. And then if we divide on both sides, we find out that Y must be 12. Okay, so that's one of the solutions we were looking for, because it did say to solve for X and Y. The other one that we're looking for is the X's. And again, you can set that up sideways. So we could do 12 is to this as 8 is to that. We could say 12 is to 8 as this is to that. I think y'all are kind of getting the idea here. I'm going to do 12 is to 2x plus 3. So I'm going sort of in this direction, if that helps. And that ratio must then equal this direction, so 8 over x plus 5. Okay. and then we can cross reduce here. I mean cross multiply. I did not mean to say cross reduce. You cannot do that. So sorry. All right, so let's do that. So if we do 12 times that x plus 5, don't forget you have to actually distribute that. Same thing with the 8. It's 8 times that 2x plus 3. And we got to make sure we distribute those. So here we'll end up with 12x plus 60. And then here we'll get 16 plus 24. And now we can just solve that equation for x. Shouldn't be too bad now. So we can move our x's, get rid of the 12x's on both sides. It's going to leave us with 4 of them here. And then we can get rid of the 24. And so if we do that, that's going to be, what, 36? And then if we divide on both sides by 4, we find out x must be 9. Okay? And maybe some of you might have set that up differently than I did when you tried it, which is actually, I think, a really great idea, because if you might have organized it a little different, as long as you did it consistently, then your math may look a little different at first, but you should get the exact same answers, which is kind of cool. Okay, let's try number 4. And here we want to determine whether or not they're parallel. So this speaks more to this converse and whether we have the hypothesis that is required, right? So in order for us to determine if they're parallel, I need to determine if the side or those segments are proportional. So the idea here is to check for proportionality. And now you know you could do 90 over 50 and 72 over 40, 50 over 90, 40, as long as you do the same organization. So I'm going to go 90 to over 50 and say that that ratio must equal 72 over 40. And then you can either find the cross products and see if they're the same answer, or you could just reduce both of these. Like here I can see right away that these guys reduce by 10. And so if I divide all of that by 10, I get 9 over 5. So this is what we're looking for, by the way. This is a question mark. And then here I just happen to know that 8 goes into both of these. So 72 divided by 8 is also 9. And 40 divided by 8 is 5. So this does check out. These are proportional. And since those segments are proportional, then I conclude that yes, PS is parallel to QR by the converse, or by the converse of the triangle proportionality theorem. Okay? The answer is yes, and that's because we could prove those. You could also, like I said, do the cross products, check those, and you'll see that 50 times 72 gives you exactly the same answer as 90 over 40. Divide 90 times 40, sorry. And since those two products are the same, then it's proportional. So you could do the reducing, or you could test the cross products. Okay, so now we know the triangle proportionality, and we know the converse of it. Let's talk about the 3 parallel lines theorem. Okay, so if 3 lines intersect, or 3 parallel lines more specifically, if 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. So again, if we have 3 parallel lines and we have 2 transversals, then these relationships like UW to Y to WY, that ratio is the same as VX is to XZ. So you end up with a whole set of proportionality right here between these 4 sides. Okay. Let's test this out. Again, feel free to pause this, try 5 and 6 on your own, and then you can see if it worked out. Okay. So hopefully you've done that. We're going to take a look. This is what you should have gotten here. So check your answers as we go through. In this diagram, they tell you that these guys are congruent. So although they didn't just come right out and say that these lines were parallel, by corresponding angle converse, if these are congruent, then by the converse of corresponding angles, those guys have to be parallel. And if these are congruent, then these guys have to be parallel. And so those congruent angles were given to you, so you could still conclude they're parallel, even though it wasn't just given to you on a silver platter. You can still find out. Again, that's by the converse of corresponding angles. And then since those three lines are parallel and you have this transversal AC and this transversal DE, then these smaller segments must be proportional. And that lets us find DF, which is what we need. Okay, so these are all proportional. I set it up as 30 is to 35, the same way that 42, this bigger one, is to DF, which is what they wanted us to find. You could have also done 30 is to 35 as 12 is to EF, and then gotten the 12. Gotten this answer, sorry, not the 12. Gotten this, which would have been 14, and then you could have added them together at that point. Okay, but you could do the big side as long as you know one full set. You could do the big side since that's what they were asking us for, or you could have found EF and then added it to 35. Either way, you should get 49. Okay, and then check number 6 to see how you did here. Again, they tell you these angles are congruent. They didn't flat out tell us that these streets, Main Street and 2nd and South Main, they didn't tell us they were parallel, but by giving us that angle 1, angle 2, and angle 3 are congruent, we can determine they're parallel because, again, of the converse of the corresponding angles. So these guys are all parallel to each other. And as such, then these smaller segments right here that are made by this transversal and this one, they must be proportional. So what they want here is they want to find out what is the distance between this HF and Main Street. No, sorry. Find the distance HF between Main Street and South Street. So sorry. Okay. So yeah, we're looking for that HF distance here to here, from this point to that point. That's perfect. Okay. So again, if I'm looking for that bigger one, then I went ahead and I added the 150 and the 300. And I compared that to the sides that we did have information, which was the 120 and the 150. So I said 120 is to the whole thing, as 150 is to the whole thing. Again, see how it's like as long as you use the same logic for both, it works. So 120 here is to the whole thing, as 150 here is to the whole thing. You could have also done 120 is to to GH, as 150 is to 300. Found this, but then just make sure you add that 120 back so you have the full length. Either way, the full length should be 360. And shame on me, this should be in yards. Where are my units? Okay, there you go. So hopefully that's helpful. You tried it, then we went over it. Let's go through the last one. We did have one more to talk about, and it's very similar, but this one does have to deal with our triangle angle bisector. So this one is all about an angle bisector and the two segments that are created when that angle bisector intersects the third side. So if a ray bisects an angle, here in this case it's ACB, then it divides this opposite side, right? When it intersects right here, it divides this opposite side into two shorter segments whose lengths are proportional to the side lengths, which is really kind of interesting. I've always found this one to be very fascinating. So what we mean by that is once I create an angle bisector here, if I extend it far enough to intersect the opposite side, then whatever the ratio of the side lengths that made that angle, AC and CB, these smaller segments will have exactly the same ratio. And so they'll be proportional. So let's practice that. We'll do this one together, and then you can try the next one on your own. So, and then we'll finish off with this. So in this diagram, they tell you that the QPR here is congruent to RPS, and that's already marked for us here and here. So we know that PR is an angle bisector, essentially, okay? We want to use these given side lengths to find the length of RS. I really like this problem and the way that we have to set it up. Okay, so the idea again is that because this is an angle bisector and R is part of that angle bisector that intersects the third side, then the ratio of these two sides, this 7 to 13 ratio, must be equal to these two segments, okay? And this is the one I'm looking for. Now, this gets a little, excuse me, this gets a little tricky because I don't have this measure. I just have the total. So you have to get what I like to call algebraically creative here and come up with an expression, because we still have to set something up for QR here, and I don't want two unknowns necessarily or two different variables. We know that that would put us in a predicament of having to have a system. Nobody's trying to do that, okay? So we know this is, we're going to call this X, and I know the total is 15. So the question is, this goes back to algebra, how could we name this in terms of what we know? Well, if the total is 15, let's say for a moment, let's pretend that we know this is 15 and this is, I don't know, let's pretend we knew this was 8, right? How could we find QR? Well, we would do 15 minus 8, right? We know it would be the difference. If this whole thing is 15 and that is 8, then we know this would have to be 7, for example, because 15 minus 8 would give us 7. That's the logic that's going to help you set this up. We know that whatever this length is, it's going to be 15 minus x. So I can call it that and use the same variable, right? Because I know whatever this is going to be the difference of 15 in that, and together they equal 15. Now I can set up my proportion, okay? So I can say, all right, sounds good. So essentially 7 is to 13, for example. So I'm starting on the top one here, on this side. So these are going to go to this. So 7 over 13 has to be equivalent to that 15 minus x over x. So if I went from here to here, then I've got to make sure I am consistent and I do this side to this side. Okay, there's our proportion, cross multiply. 7 times x is 7x, and 13 times that difference is going to look like this. Don't forget to distribute. So when we do 13 times 15, we get 195, and then 13 times x is minus 13x here. And then all we have to do is add those 13 on to this side. That's going to give us a 20. And then we divide both sides by 20. And we find out that x has to be 9.75 here. But that's not what they wanted. We needed it, but what they really want is a length of our, oh no, that is a length of ours. Just kidding. Just ignore me. There you go. There it is. Okay. So that is our setup, okay? All right. Oh, now y'all can see that. So that one is definitely a little trickier. Go ahead and pause it and try number 8 and see how that goes. And then you can check your work, and then that will be the last one here. Okay, so hopefully you had enough time there. In this one, we want to find the length of this xy. Now we know, again, this is 24. The whole thing is 24, and this is what we're looking for, okay? And let's see, we know it's an angle bisector, so let's go ahead and set this up. So if we did this correctly, you could set this up as 15 is to 21, the same as, let's call this, I guess, x, or you can even call it xy, that's fine. But then this side has to be 24 minus xy, right? Whatever that difference is, cross multiply. And then here we get 15 times xy. And then we just distribute and solve. So this is going to be that. 15 times 24, I think it's 360, but let's find out to be sure. I'm pretty sure it is. 15 times 24, yep, 360. And we distribute that guy, and then we add the 15 over. That happens to be 36 times this, equals 360. And now you can see it's going to be really easy. When we divide here, we find out that the length of that xy must just be 10. Okay, so that sets that one up. And sometimes they will give you, one of the answers, not just the total. These are a little harder, which is kind of nice because then the other ones will feel easier. But that is all of 8-4 as a lesson.